4:50, and so I shall start. So welcome everybody to my tea time talk. This is going to be some preliminary work that I've been thinking a lot last couple months. I think the calendar title was something like Continual Learning, Linearity, and Scalability. I couldn't really think of a better title at the time, but in working on the slides, I came up with this, Continual Learning with Linearity, from viable to scalable. So let me start by talking about some criteria for a continual learning algorithm. And I'll be clear, this isn't my idea. This is actually titled like 3 initial ingredients for continual learning in Mark Ring's PhD thesis on continual learning in reinforcement environments back in 1994. And so he lays out 3 criteria, the minimal viable product for a continual learning algorithm. And so I'll quote him and then kind of summarize it with a word that may or may not be his own words. The first part that you would need is for the algorithm to be autonomous, at least to some degree. And so you want it to act without human intervention, or maybe learn without having a human in the loop. You want the algorithm to be plastic so that it can acquire new behaviors when they're useful. And most importantly, you want this to be sustained. So you want those properties of autonomy and plasticity to span arbitrary periods of time. So the question I'm going to be asking is, what's a viable algorithm for continuous supervised learning, given that we want these 3 things, for the algorithm to be autonomous, plastic, and sustained? I'll first kind of describe what type of supervised continual learning problem I'm going to be mostly focusing on. And so in continual learning, in the supervised setting at least, we take a data set and we combine it with a non-stationarity. In this case, I'm going to use MNIST. It's very simple. We have these digits corresponding to these images of digits, and each of them are assigned a randomly given label at the beginning of some task. And so an agent or algorithm faced with this needs to learn to memorize these given random labels, and it's given some fixed amount of iterations per task, in this case, t. So after the end of the first task, the algorithm would have done t total iterations and have learned to memorize a couple of these random labels. After t iterations, we have a new task, task 2, where the labels for the MNIST observations are randomized again, and the task faced by this algorithm is again train for t more iterations and try to memorize these new random label assignments. And so from the beginning, the initialization of the algorithm way back in, let's say, task 0 up to task 2, there have been 2 times t total iterations. And this can continue because there's many different observations, many different assignments to these labels, to say like task k. And at task k, we still want the algorithm to keep learning to memorize all these random labels. And we have the algorithm would have done a total of k times t total iterations. So what's a viable continual learning algorithm for this random label MNIST problem? Well, by design, the problem is autonomous. Or the algorithm is autonomous because I'm only giving the agent information corresponding to the observation and the label associated with that observation, not anything with the task, and I'm not allowing like resets for the network or the algorithm. So for an algorithm to be plastic, it needs to be able to memorize the labels in a given task. And for this to be sustained, it needs to keep learning adequately on future tasks. So the question is like a neural network trained with SGD viable? Does it fulfill these 3 criteria on this problem? So I'll be showing you very quickly the online learning performance for neural network with ReLU activations. So early on, we're able to the network is able to memorize a good portion of the labels. So this would be maybe at the end of the first task, not exactly because this is a bit smooth. But then as more iterations, as the algorithm runs for more iterations, more tasks are encountered, and eventually it's no longer able to memorize these labels. So maybe halfway through training, it has lost all of its plasticity. What about a linear baseline? So in this case, I'm just using linear function approximation. On the first task, it's able to learn something, not as well as the ReLU network, but something nonetheless, and that is able to be sustained throughout its lifetime. I'm going to abstract away from this plot, where instead of plotting on the x-axis the number of iterations, and on the y-axis the online accuracy, I'm going to be summarizing this information in terms of the end of task accuracy, and on the x-axis the number of tasks. So this conveys the same information as the earlier slide, but just abstracts the online learning performance and just shows that at the end of a task, a linear baseline can sustain the performance that it had in the beginning, whereas a RLAI network cannot. So we might conclude, at least in this problem, that a linear learning algorithm is viable. Yes, question?
Isn't the problem kind of weird because there's no relationship between the label and the actual picture?
Yeah, it is kind of weird. It doesn't have any generalization structure, so you can't really evaluate like test accuracy. What I'm really looking at is the trainability of these algorithms. Can they keep memorizing these random label assignments to minimize their training error? And if they can't, then of course they can't even generalize. But you're right that you could, in practice, in principle, like memorize all these labels or minimize your training error and not necessarily generalize. That's a separate question I'm not going to be addressing today. Yes?
Is the label of each one example being randomized, or each like number, as in all the ones are now 2 or 4?
The first one. So we're only going to be randomizing on each observation. So for a particular class label, like let's say 7, you can see like this image of a 7 is assigned a random label of 1, and this image of a 7 is assigned a label of 2. So completely random labels. So this is a pretty simple problem. And yet RLAI networks are unable to keep memorizing these labels, whereas linear is. And so we might conclude that a linear learning algorithm is viable in the sense that it's autonomous, plastic, and that can be sustained. But I want to go one step beyond viable and ask, what about a scalable learning algorithm? So in this, I mean, kind of more generally, improves with additional resources. What are resources, you may ask? Well, in this case, since we're thinking of gradient-based learning algorithms, we might think of iterations or something to do with the parameters of your neural network, the depth or the width. I'm going to focus first on the number of iterations. Yes, Vlad?
For just to understand the sustained one, it does not mean that when you face the same problem again, you like immediately remember how to solve it.
Yeah. So in this instance, there is no sense in which you could do that because the labels are being randomly assigned. But you can imagine another problem. Maybe you learn some general feature that persists across tasks or something like that. Then that feature, if it's sustained, that could fit that third criteria. Okay, so scalability. I'm going to be focusing first on the number of iterations per task, that capital T that I described earlier. So the lighter lines correspond to like algorithms with less resources, in this case, 20 epochs per task. And the darker lines have more epochs per task. So this is more iterations done on a given task. And we can see that if we give this RLAI network more iterations, from 20 to 40 to 80, it's doing worse. It's doing better initially, but in terms of its ability to sustain that performance, it's doing worse as we give it more iterations. So it's not scalable. This RLAI network is not scalable with respect to the number of iterations. What about linear function approximation? Well, linear function approximation is because although there might be some drop off in performance relative to the beginning, the performance floor increases as we give the linear learning algorithm more iterations. And again, this is a simple problem. I'm not even using all of the MNIST observations. I'm using a very small subset so that linear can fit this task if I were to increase the iterations up to 1,000. So I'm going to summarize all that information in this plot, where now on the x-axis, I'm plotting this number of epochs. So from 20 to 40 to 80, the linear learning algorithm is able to improve its performance, whereas ReLU degrades. And so I want to find algorithms that have this property of scaling, improving as I give it more resources. And at least for linear function approximation, this seems like a potential candidate. Yes?
Is the lowest performance level the same as random guess?
Yeah, random guessing would be somewhere around here, like 10%, 10% accuracy. So if you lose plasticity or whatever, eventually you're going to be defaulting to essentially random guessing on random labels memorization. Yes?
So when you talk about it improving by giving it more resources, when you're not doing a function approximation, of course, you don't need to do it iteratively. You could just solve it in first form. Isn't it a little bit weird to first inflate the amount of resources it needs by using a sub-optimal algorithm and then like giving it more resources?
Yeah, I see what you mean. It's like resources are kind of specific to a particular choice of algorithmic family, right? Like iterations doesn't really make sense for something like, I don't know, solving the system of linear equations or something. But for gradient-based algorithms, iterations is like a valid measure for research.
But what if somebody came to you and said random forests are going to do really well on this?
Yeah.
And then, yeah, it seems hard to like account for what the resources are.
Yeah, that's great. So that would be an algorithm that doesn't scale in that regard. And so either you could say that the comparison is like just not compatible, like you can't compare these two algorithms, or you might say that I want an algorithm that does scale with these iterations if I can afford them, right? It depends on the problem in the algorithm, this relationship. Okay, so I was talking a little bit about scaling with number of iterations, and now I'm going to be talking about scaling with depth and width. This is kind of weird to think about for linear function approximation because given some input dimensionality and some output dimensionality, I have one matrix that fits those requirements. Depth and width doesn't really make sense. But instead we can think of not neural networks, again, they're a whole nonlinear mess, but we can think of deep linear networks, which are somewhat between linearity and nonlinearity. So what do I mean by this? Like a deep linear network just takes a neural network and removes the activation function, that nonlinearity between layers. And so what we have is like a product of these weight matrices, theta L minus 1, theta 1. So this has like a depth because we have L parameter matrices multiplying each other. And there's a width associated with them because the hidden dimensionality, like theta L minus 1 or theta 2, can be wider or narrower. And so why do I say this is somewhat between linearity and nonlinearity? It's linear in the sense that it can only represent linear functions. You can just multiply all the parameter matrices into one matrix, and then it's clearly a linear function, right, with this parameter. But it's nonlinear in the sense that if you're wanting to update these parameters, theta L minus 1, theta 1, the gradient dynamics are nonlinear. Because if you take a gradient with respect to any one particular parameter, it depends on the parameters of the other layers. And so these gradient dynamics are similar to deep nonlinear neural networks, but representationally they're linear. So the question is, like, for continual learning, does a deep linear network sustain plasticity kind of similar to this like shallow linear function approximation? Or do we like lose plasticity similar to like deep nonlinear networks? So same idea, we're going to take this deep linear network. There's some parameterization that's not so important. And we're just going to increase the number of iterations, and we see that we get this increase in the performance floor with additional resources, similar to shallow linear function approximation, which suggests that, at least for this problem, deep linear networks are kind of more similar to shallow linear networks. One nice thing, though, about deep linear networks is that we can actually increase the depth and width and get scaling in this regard. So similar to the other plot on the x-axis, instead of plotting the number of epochs, I'm plotting the depth. So it goes from 1 to 2 to 3. So not like very deep or anything. But as we increase the depth, the deep linear network actually improves with this resource, whereas regular networks don't. We can show something similar for width, where if we increase the width from 128 to 256 to 512, deep linear networks scale in this regard, and again, regular networks do not. So deep linear networks are scalable, perhaps a scalable approach to continual learning, but they're representationally limited. So ideally, we kind of want like a network that has some properties of linearity, because we have this nice empirical result, at least, that we can sustain performance. But we want to predict complicated things. We want nonlinear function approximation because our problems are more complicated than a tiny little subset of MNIST. Does anybody know who these characters are?
Sherlock.
Yeah, it is. It's like the original illustration. So I was trying to find like combinations of characters that might fit this regard. This isn't perfect, but you can think of like Sherlock Holmes as, quite a complicated fellow, make very interesting predictions that you can't really explain, but he's right more often than not. And then there's Dr. Watson, who's also very intelligent, a medical doctor, but he's a bit more interpretable, a bit more personable. He's a bit more like a linear function approximation. And so if you want to succeed in solving crimes, maybe you want both of them. You can't have just Sherlock Holmes or just Dr. Watson. And if you're not familiar with the original illustration, there's like the BBC series that might be more familiar. Okay, so does anyone want to throw out some suggestions on how we could have more linearity in a neural network? instead of ReLU, maybe we have something else.
Residual connections.
Yeah, residual connections is a good idea. Residual connections add linearity from the input to the output mapping. The identity function, that would be like the deep linear thing. Yeah, so those are all things that I was thinking about, and not what I'm going to be talking about. But instead, we can do something called what I'm calling adaptively linear networks. It's a kind of a cute name. The acronym is just AdaLin, which is nice. And the idea is just to use deep Fourier features. So this is basically using an activation function, which is a concatenation of the sine of the pre-activation and the cosine of the pre-activation. Why is it adaptively linear? Well, for a given pre-activation value, in this case, like between -π/4 and π/4, sine is approximately linear in this region. So this is like the tangent approximation at 0. Whereas cosine is kind of nonlinear, or kind of quadratic. And so for a particular pre-activation value, we'll have either that sine is close to linear and cosine is kind of nonlinear, or the other way around. So depending on the value of the pre-activation, we'll have one component of the activation function being like kind of capturing this linearity, and another that doesn't. So this is the idea, try to balance linearity and nonlinearity through this like choice of activation function. And so how does it do? So I alluded to earlier that random label MNIST problem was small because a linear function approximator can fit it. If I were to use the whole set of MNIST observations, linear isn't going to do very well. But the function is too complicated to learn, and linear is just representationally limited. It can't capture that function. With ReLU networks, as we saw before, it's great, like at least initially. Then you get this drop off in performance due to like loss of plasticity. There's another activation function that's a bit more linear than ReLU, leaky ReLU. You can try that too, but you also get this degradation in performance. Yes?
Right. I was looking at the previous slide and the sine and the cosine. Wouldn't it be like more straightforward to just have x and x squared instead of something that approximates to x and something that approximates to x?
Yeah, I was trying that too. Yeah.
And then you can try the same as like the quadratic polynomial basis functions like.
Yep. Yeah. So I was looking a little bit at like these combinations. There's a couple other things you can do, like take a ReLU and the negative ReLU, like a concatenation. So one side is always active and linear. What tends to happen though is like, say all your activations are quite large, then you get like a collapse of like the nonlinearity on one side, and you either have like a completely linear network or something that just doesn't behave well. But one of the good things about this is that for because of the periodic nature of sine and cosine, like even if the pre-activations are quite large, you still get this like shifting between one component being linear, the other being nonlinear, and they can alternate between each other.
So the pre-activation has to be the same for both the sine and the cosine. Like, you don't have independent pre-activation.
No, yeah. So for every pre-activation, we have both the sine and the cosine. That's key. Okay. So linear ReLU, leaky ReLU. So ReLU, leaky ReLU, suffer from this loss of plasticity problem. Linear is like not enough. What about like a small adaptively linear network? So a small network is not that great at the beginning, but it does improve over time, which is promising, right? Like usually we see either constant performance or a degradation in performance. Seeing something increase is quite novel, at least in the context of this presentation. We can increase the size of that adaptively linear network, so like to a medium size. And again, we get slightly better performance in the beginning, but more importantly, we get like an improvement as more tasks are encountered. Again, something that wasn't featured in the previous examples. And then we can take something like a big adaptively linear network, which is not that big in the context of compute these days, but for this problem was quite large. And again, although we don't have the match the performance of a ReLU network on the first task, as more tasks are encountered over the course of continual learning, you actually surpass the performance initially with a ReLU network. And so I'm going to show just very quickly some scaling results, similar to what I've shown before. If you increase the number of epochs for some adaptively linear network, you get an increase in performance almost linearly. Same with depth. So as you increase the number of layers in this adaptively linear network, you do get a performance benefit up to some point where it's sufficient to solve this problem. And similar with width. If you increase the depth and width and the number of iterations, you get better and better performance, at least in the context of this problem. Okay, so closing thoughts. In supervised learning, linearity seems like a viable approach, and deep linearity seems scalable in the sense that I described. And these deep Fourier features are able to adaptively balance between these benefits of linearity and simultaneously nonlinearity, improving scalability and representational capacity. Some things I did talk about that I was kind of excited to is like formalizations around this problem. What does it mean to be viable? What does it mean to be continually trainable? And also some like theory for continual learning with either shallow linear function approximation or with deep linear networks. And some future work that I've been thinking about is what exactly does this linearity provide for like a non-linear function approximator? I only have like intuitions that linearity is good and you need some non-linearity, so let's combine them, but I actually don't know exactly what it is that linearity provides. And applying this like adaptively linear approach to other architectures and blocks like a convolutional neural network or a recurrent neural network or like an attention block, these are things that I'm quite interested in pursuing. And lastly, I was showing applications in like this very small supervised learning problem. I'm interested in applying it to more broadly to reinforcement learning and like problems that require complicated changing prediction. And so that's my talk. Thank you very much for listening. Eden?
Yeah, thank you for the talk. So there are, it seems like in this problem, or the task you gave us, the main problem was sort of plasticity, right? And there are a couple other ways of fixing that now. Are there any other insights that I should be like really taking away? Or is it this just like another alternative method of achieving that same maintaining plasticity?
Yeah. So there is like, there's two goals, I think, to this work, for me at least. It's understanding a bit more, this talk wasn't about this, but for me it was understanding theoretically what we can say about plasticity in algorithms and being able to show that at least with some assumptions and shallow linear function approximation, we can maintain plasticity. That was kind of like the bedrock of this. So just trying to understand what is it about linearity that allows us to maintain plasticity. The other thing that you mentioned, like there are other methods to prevent loss of plasticity. In the paper that I was working on, also looked at like different regularizations and resetting. The benefit of this approach is it's like scalable in the sense that those approaches might work, but they may constrain the network. Like if you regularize or like reset neurons, you're kind of like wasting some computation. If you reset a neuron, everything that I learned before just vanishes, right? Like it doesn't persist. And if you regularize a network, you're kind of constraining the way that the parameters can move. And so maybe that can, again, I don't have evidence in this talk for that, but that can like restrict how much you can learn in a given number of iterations. This kind of sidesteps that, right? Like we're able to just increase the number of iterations or the size of the neural network and still get these benefits. Combining the two, it seems like you don't even need regularization for this type of neural network. Whereas in my AI seminar, I'll talk about spectral regularization, which you do need for like a regular network to prevent loss of plasticity. Vlad?
Did you try increasing the size of the Revo network?
So for the larger problem, I didn't, right? Like I didn't even bother. I gave it the maximum size that allowed the adaptively linear network, and it already lost plasticity. In the smaller problem, with a linear, where linear was enough, in that I showed if you increase the size of the network, you actually do worse, right?
Okay.
Yeah. Yes.
Did you evaluate the accuracy on each task separately? Or?
Yeah, so the evaluation was done at the end of a task. I take all the observations, the labels from that task, get my accuracy. So it's kind of like this batch offline evaluation at the end of the task. I was also plotting like the online accuracy very early on. There's some differences in the way that the problem can be phrased, either in terms of like this online or offline evaluation, and there's trade-offs. If you want to get into that, maybe we can talk offline.
Okay, like in this case, like can we say that like linear methods are good for getters instead of saying that they don't lose plasticity? Like when they are introduced with new tasks, they just forget about previous tasks. But through continual learning, like new tasks are being introduced online, and you have to learn them without forgetting the previous tasks. So your performance on the previous tasks would worsen as new tasks are introduced.
See what you mean? Like there is a sense in which you might think plasticity and forgetting it, there's a trade-off, right? That's assuming that we're at this Pareto front where we're optimally trading that off. I suspect that's not the case, and so I don't even worry about forgetting yet. This problem is designed that like you don't need to remember anything, right? It's not necessarily the case that the RLAI network is memorizing everything from before. I haven't looked into this for like this linear function approximation setting, but if I were to plot the accuracy on the last task, then it will go down as you train on the new task, but that's what you want because the observations are the same. The labels have changed. You have to undo your predictions, right? Forgetting is important, but not within the scope of my work right now. Yes?
I was thinking about this older paper from George Contreras, where he talks about a Fourier basis function in the context of RL. I think in his case, you get this input vector, and then each element in the input vector, so you get Fourier features for that. But in your case, you're talking about applying it as an activation for each of the units.
Yeah.
Did you try comparing the two by any chance?
Yeah. So there's even more recent work like looking at Fourier representations like signals, and in particular for reinforcement learning. So it's kind of like using either a fixed Fourier basis or maybe like a learned Fourier basis on like the first layer. It's key that it's on every layer because if you were to transform the signal into like these sines and cosines, but the rest of your network is ReLU activations, you still get like this loss of plasticity, like these dying neurons. So. Yes.
I'm interested in like in practice, do you notice that your network is like faster to perform inference on? Are you using fast Fourier transforms, or are you just doing sine cosine of the activations?
Yeah, I'm not doing anything fancy. I'm just calling sine and cosine. I imagine it's more expensive than ReLU, but probably not that much more expensive. I'm not sure. Yes.
Yes. So I want to ask you about your network with the AdaLin network, and like, why is it improving over time? Like, that's a bit strange. Is there? I would imagine without recurrence, it's sort of hard to see a case where that would happen.
Yeah, it is puzzling. Actually, something that I didn't want to dwell on was exactly this point. Even if I run like the deep linear networks for enough tasks, you actually do see an increase in performance. It's kind of marginal, but it's there. And there is some theory work trying to understand what the benefit of depth is. And what they found is that the hidden layers of your neural network can act as like preconditioners to accelerate gradient descent. And so I suspect something similar is happening. Like you don't get any benefit from learning from previous tasks because there's no shared structure between the problems, but you might just be getting some acceleration over time just because of the way that the neural networks have kind of configured themselves. I don't know, it's kind of mysterious. I'd like to look into it more. Yes.
So you mentioned about the formulation of the problem, like the criteria by like a thesis in the past. So the first point of that where it says it should learn autonomously, like no human intervention. But how about we have this problem where it's a human in the loop problem, but the agent is also expected to kind of learn continually. So for example, like if I have like a cleaning robot, for example, and that has some baseline amount of knowledge, and then there's a human in the loop which is there to instruct it in the house. So that's a human in the loop, and it's also expected to learn continually, improve its behavior and adapt and so on. So how do you think of that in context of the definition that's given there?
Yeah, so the definition is loose and based off of like some prior work, but it's one set of minimal criteria that, if satisfied, does provide an algorithm that seems like it would be a good candidate for learning continually. It can be lucid, right? Like you don't need to be fully autonomous, but you do want, if there was no human loop, for the algorithm to just function adequately. You can also think of like human interaction as a resource, right? If an algorithm can do better by like being supervised more, then sure, that I think scaling with that is great. We clearly benefit from the people around us. some people are able to use that better or not, and that's just these types of trade-offs that we have to make in our algorithm design. It's difficult to think about though, right? I can't really quantify how valuable a particular interaction with a human is, so I'd rather not think about it. Yeah. Someone in the back, yeah.
When you say what does linearity provide for non-linear structures, what do you mean? I thought linearity kind of provides scalability.
Yeah, so there is this performance benefit, like the scalability benefit of adding linearity. I mean, like more structurally, like what is it that linearity provides? Let's say for the optimization problem, does it make the optimization problem easier? Is there some sort of implicit regularization? Like, what's the mechanism that linearity provides that is not otherwise present? What allows linearity to get this benefit of scale? That's the mystery. Yes.
Does it work with just sine or cosine activation?
Yeah, so it's meaning to include those results here. I've seen mixed results. Sometimes sine alone is enough, but you might need to scale down the size of your step size. Like maybe it doesn't so it doesn't get too large. It stays within that linear region. I've also seen even with a tanh activation, around the origin is also kind of linear, similar to like a sine function, and that also allows you to learn much longer than like a ReLU or a leaky ReLU network. I need to investigate that a little bit more. Yeah. Yes.
So in the plot where you compare AdaLin with others, is it a correct interpretation to say AdaLin is learning slower than the others?
It depends on what you mean. I'm not plotting like the online error. So I'm within like the first task, clearly it's learning slower, or at the very least like not able to. Yes, I think for the first task, it's correct to say that it does learn slower. But in terms of like continual learning performance, like over more tasks, let's say, then in that sense, it's learning faster, right? Because eventually it's be able to do better.
I also wonder if we expand the duration of the experiment, is it going to eventually fall down like the others or what?
Yeah, so I ran some of these experiments, not for like 50 tasks or 500 tasks, but 5,000 tasks. And if your step size is too big, even with this, you can get very large weights, like instead of having weights that are below one, you have weights above one. And at that point, you start getting instability. So in that sense, you might still need some regularization, but it recurs like thousands of tasks down the road. Usually like a larger scope than is featured in current like continual learning experiments. Yes.
I mean, the same thought would, if you were to place the big, deep linear line, where would it go?
Big, deep linear. This is big, deep linear, yeah.
Oh, that's the deep
yeah. So yeah, I use the same color for linear and deep linear, but you're right, yeah. So this is the same size as the biggest AdaLin and the same size as leaky ReLU and ReLU. So it's like 3 layers, 512 depth. So, okay, not huge, but because it's still linear in its representational capacity, it can't learn to predict all these labels. It's not linearly separated. Yes, I think last question.
So you mentioned you also look at the base and their magnitude. Are there other properties that you've been looking at for all of these methods? Yeah,
so it was something I was interested in understanding, like what are the properties that are gained or lost or whatever. It definitely seems like if your weights grow indefinitely, eventually you'll run into problems, like at least numerical stability issues. For AdaLin, what I can say is like a lot of the properties that I was looking at before that seem to correlate with loss of plasticity don't occur, in a sense that like with the sine and cosine activations, you usually have high feature rank. Your Hessian is usually like pretty well behaved. The only problem that I see is that the weights can still grow over time. So some degree of regularization might be important. Okay, thanks everyone.